Okay, today's lesson is going to be on probability. That's what 3.4 is. Specifically, we're going to talk about with versus without replacement. There's going to be questions where we do multiple trials or multiple, uh, whether we're drawing a card from a deck or rolling a die or pulling marbles out of a bag, whatever it is, we're going to do multiple trials of that experiment. And we're going to talk about with replacement and without replacement, and what is the probability of having certain things happen one after another. So, if we're drawing cards out of a deck, we're talking about things like you're going to draw two cards out of a deck. What is the probability that they are both spades, for example? So, things like that. First thing we need to know is whether or not the process is being done with replacement or without replacement, because that's going to drastically change the calculation that's being done for the probability. So with replacement, means that each trial, and I'm calling it a trial, this is just each time an action is done in the process. So each trial is independent, meaning with replacement means you're putting whatever you drew in the first trial back into the sample space. So each trial is independent, meaning that the sample space is reset after each draw. Right, I'm going to call it draw there. It's not necessarily drawing. If you're rolling a die, then it's after each roll. Whatever it is, the sample space is going to reset after each action. For without replacement problems, these are things like if you draw a card out of a deck and then you keep that card and then you draw a second card out of the deck. What happens is because we drew that first card and we didn't put it back, the sample space is now different on the second card draw. So depending on what the first card was, the probabilities are going to be different for that second draw. So on this one, trials are dependent on previous actions. Also, the sample space changes after each draw. The whole idea of manipulating the sample space, whether you're resetting it after each draw or altering the sample space after each draw, is going to be the best way to kind of tackle these types of problems. And what we're going to want to do is we're still going to multiply fractions for each probability. But we're going to keep track of whether or not the sample space has changed and modify our fractions accordingly, because we know that each probability is some form of a fraction, right? So the fraction is either going to have the same denominator sample space, or it's going to be altered because we're doing a without replacement question. So let's do a couple of examples here so we can get an understanding of what types of questions we're going to see in this section. Example here will say that if two cards are drawn from a standard deck of cards, find the probability that the first card is red and the second card is a spade. And we're going to do this in two parts. Part A is going to be with replacement. And part B is going to be without replacement. So with or without replacement, it doesn't really matter which one you're doing as far as the first card is concerned. When you draw the first card out of the deck, there are 52 cards in the deck, and you know what the composition of the deck looks like. If you don't remember, go to page, what was the page in the workbook? Page 35 in the workbook. Gives you all the information about the deck of cards. So let's do the with replacement example first, where for the first card, we're going to have, so we're doing the fraction for the probability that the first card is red will be the number of red cards in the deck divided by the total number of cards in the deck. So what's my fraction going to be for the first probability? The probability that the first card is red is good, 26 out of 52, or we can simplify to 1/2. I'm actually going to show it as 26 out of 52, and I'll show the simplification process where we divide both the top and the bottom, so they become a 1 and a 2. Times, for the second card, since we're doing a with replacement example here, we're putting that first card back into the deck. Right, whatever it was a red card, we're assuming, but we're going to put it back into the deck, and we're going to draw a second card, and we're going to write the probability that the second card is a spade. So what's the probability that the second card is a spade? Good, 13, because there are 13 spades out of 52 cards, because we put that first card back in, so there's still 52 cards. And this one reduces, like some of you are saying, this one divides by 13 on top and bottom, so we get 1/4. When we multiply those together, we get 1/8. Right, so that's the probability that we get a red card, and then the second card is a spade with replacement. Now, without replacement is going to be slightly different. Again, the first card we draw is not really affected by anything beforehand. So we have a full deck of cards. What is the probability that the first card we draw is red? Well, we just did this, right? 26 out of 52, which again reduces to 1/2. But then when it comes to the second card, we're now putting this first card back into the deck. So that first card we took out, the red card, is staying out. Therefore, our second fraction is going to be slightly different. what is the probability that we get a spade on the second card, as meaning how many spades are there in the deck and how many cards are there total left in the deck. Good, 13 out of 51. It's 51 because that first card is out of the deck. It's no longer in the deck, so sorry, that doesn't reduce to anything. So we end up with, when we multiply those fractions, we end up with 13 out of 102. Are there any questions on that example? With or without replacement? Okay, let's do another example. Let's do the probability that they are both cards drawn are diamonds. And again, we'll do with replacement and without replacement. I'll give you a minute to work on this. I would reduce them. You can also, I mean, you guys get to use calculators, so you can plug it into your calculator, multiply the fractions, and then get the result as a fraction or a decimal. Either way is fine. If you're going to give a fraction as an answer, it should be a reduced fraction. Otherwise, you can reduce beforehand or after the fact. Go ahead and work on this example. Find the probability that they are both diamonds. Okay, let's talk about with replacement here. With replacement, essentially the two fractions are independent from each other, so the probability that the first one is a diamond and the probability that the second one is a diamond should be the same, right? So if the probability that the first card drawn is a diamond is 13 out of 52, we put that diamond back. What's the probability that we get a diamond again on the second draw? $13 out of 52 again. Good. Which, if you reduce these, that's a 1/4. That's another 1/4. So we get 1 out of 16 for the probability that both cards are diamonds. Without replacement, on the other hand, the first card we draw, the probability that the first card drawn is a diamond is 13 out of 52. But what about the second one? If I don't put that first diamond back, what is the probability that the second card is also a diamond? seeing a couple of different answers. I saw 13 out of 51, and now I'm seeing a bunch of 12 out of 51s. Can someone explain why yours is the correct answer? Whoever's more confident. Is it 13 out of 51 or 12 out of 51? 12 out of 51 since it lost a diamond and the whole deck lost a card. Good. This drops to 51 because one card is missing from the deck, but specifically because we needed that first card to be a diamond, one of the diamonds is also missing. So there are no longer 13 diamonds in the deck, there are 12 diamonds in the deck. So when you're doing the second card, you assume that the first card was the card that you're doing the probability for. All right, so there are no longer 13 diamonds in the deck, there are 12 left. So this reduces to a 1/4. And then this one actually divides by 3. This divides by 3, 4 over 17. So we get and then the 4s we can cancel. So we simplify all the way down to a 1 out of 17 probability of getting 2 diamonds if we don't put the first card back. Any questions on any of that?